it's important that students learn to balance nuclear equations. But before you can go about balancing nuclear equations, you need to know the pieces that go into a nuclear equation. Okay, two kinds of particles in the nucleus. They are, everybody knows this, right? Protons and neutrons. No. For an atom, now this is not an ion. An atom is neutrally charged, meaning it has as many positive charges as negative charges. Those charges then cancel each other out. If you have whatever number of protons you have, then you have to have an equal number of electrons which are negatively charged. They're the opposite of each other as far as charges are concerned. So positively charged particles have to equal negatively charged particles for it to be neutral. Atoms are always neutral, so if you know the number of protons, you know the number of electrons in an atom. Okay, not in an ion. Ions have an uneven number of electrons and protons. Okay, so if I have manganese, an atom of manganese, and it has 25 protons, that's what that atomic number means there, then I must have also 25 electrons, okay? But, of course, electrons are not in the nucleus. Electrons are in the electron cloud around the nucleus, okay? All right. So we're talking about nuclear chemistry, and we don't talk about it a whole lot. We just spend a little bit of time in this unit talking about nuclear chemistry. We're talking about protons and neutrons. But we also talk about some things that affect those protons and neutrons. And so for those things, you need to know about some particles that exist. Now, we did a lab yesterday where we looked at some little gas trails, okay, some vapor trails, all right, in a gas chamber, right, cloud chamber. And so what we did was we put some ethanol in there, and we put it in a little chamber on top of some dry ice. And what you can't see that was happening there was the ethanol was forming little tiny droplets. It was evaporating, as ethanol tends to do. Okay, and then it would, all those little molecules that are start to stick together in little tiny balls, and they're floating around in there, behaving like the particles that Einstein described for Brownian motion. Okay, they're just floating around in there. They're just like clouds in the sky, only we can't see them in the cloud chamber. But when you shoot a alpha particle through there, they sort of gather and clump up, and you get this little cloud you can see. Okay? And so that is what you saw. You saw evidence of, not direct visual sighting. You didn't observe an alpha particle. It's far too small. We don't have a microscope powerful enough to see alpha particles here at Dorman High School. In fact, there's no microscope anywhere around here powerful enough. Even electron microscopes that they have at some of the colleges around here, because alpha particles don't sit still long enough to see them. Okay, so they're moving really fast, and they're too small to see. And what they're made up of, alpha particles are made up of 2 protons and 2 neutrons. Okay, so they're just like the nucleus of a helium atom, or at least most of them. Most helium atoms have 2 protons and 2 neutrons. Not all helium atoms do. That's why we have an average atomic mass that was described in the video there. Average atomic mass means you take all the isotopes of an element and take their relative percentages and figure out the overall average for all the known number of those isotopes in, at least where we are in this part of the universe. Okay? And so you get an average then. That's why you have these fractional numbers at the bottom of the periodic table symbol here in this box where everything is. Okay, here's our number of protons. That's exact. But the number of neutrons can change from one atom of helium to the next, although the vast majority of them have 2 protons and 2 neutrons, thus an atomic number that's pretty close to 4, an average atomic mass rather, that's pretty close to 4. Okay, now, so alpha particles have 2 protons and 2 neutrons, but the difference between an alpha particle and a helium atom is helium atoms have electrons. Okay, so an alpha particle has a positive charge because there's no electrons to balance out the two protons there. All right, got that? And these alpha particles are why smoke detectors work. Okay, there is stuff in a smoke detector that is radioactive. Americium. That's what you have in a smoke detector. You can find americium on your periodic table. Anybody see that? Oh, there it is. Okay, and that stuff is constantly radioactive. It's giving off these alpha particles. Those alpha particles are charging a target or plate in there. And as long as that charge exists there, and it doesn't last very long, alpha particle gets on there and it falls off somewhere, okay? And so if you stop hitting it with alpha particles, it stops getting charged. And if it stops getting charged, then the smoke detector goes off. And the key thing about alpha particles is that they're not very strong. I mean, they wouldn't even go through this piece of paper right here. Okay, that's why when you were doing your cloud chamber lab, you had to make sure that the ethanol we're using didn't soak the outside of your uranium ore sample. Okay, because if it soaked the outside of your uranium ore sample, that liquid would stop the alpha particle. And that happened to at least one lab group in here. Okay, they didn't see alpha particles because their rock was wet. Okay, got that? So alpha particles aren't very powerful. All right, so the only thing that's actually giving out alpha particles that we saw, or for which we saw evidence of yesterday, was those uranium atoms that were right at the surface. Because if it's down inside, they didn't come out. Okay? So they're not very powerful. Can we stop that, please? Thank you. All right, so that's what an alpha particle is. Now, if you take an alpha particle out of an atom, that atom is losing 2 protons and 2 neutrons. So, if we have a uranium atom, okay, and let's say we're working with uranium 238. 238 is not the most radioactive form. The kind that you want to have a lot of if you're going to use it in a nuclear power plant or a nuclear bomb is 235. But 238 is the most common. So if we have uranium 238 and it has a mass of 92, now this is called a nuclear symbol, okay? A nuclear symbol, all right? This is how we write it. The mass goes at the top, the atomic number goes at the bottom. This is how you have to write nuclear symbols. I hope you're writing this down. If we take out of there an alpha particle, and an alpha particle symbol is this is a lowercase Greek letter A, lowercase Greek letter A, okay? We have an alpha particle. And alpha particles have an atomic number of 2 for 2 protons, and its atomic mass is 4. Add up all the protons and neutrons, you get the atomic mass, 4. Okay? Then, if we take that out, what do we have left over? How many protons are we going to have left over in the particle that remains? 90. And what atomic mass are we going to have for the particle that remains? 234. See, this isn't hard, is it? Okay. Okay, so what element has an atomic number of 90? This is where you need to get out your periodic table if you don't already have it out. Notice how much we use our periodic table? All the time. Thorium. So every time those uranium atoms in your sample yesterday went through alpha decay, a thorium was created. Okay? Got that? These are called nuclear equations. These are called nuclear equations. Okay? Alright, so those are alpha particles. There are also beta particles. Beta is the second letter in the Greek alphabet. Alpha is the first. Okay? Beta particles, for all practical purposes, beta particles are the same thing as an electron. Okay, they are a little tiny, really tiny, negatively charged particle. So electrons and beta particles are almost 2,000 times smaller than a proton or a neutron. Neutrons and protons are about the same mass and size. Okay, in fact, they're not. Their mass can't be perfectly determined, but beta particles are 2,000. Really, it's a little less than 2,000 times, but that's a round number, easy to remember. Okay, 2,000 times smaller. All right, so there's almost no mass. Now, a beta symbol, lowercase b or lowercase beta, looks like a bee, doesn't it? Kind of with a tail. All right, I've got a B with a tail. Capital B with a tail. Script B with a tail. Okay? Well, that has almost no mass. So what are we going to put up here at the top? 0, because there's almost no mass. Okay? But, it would probably be 0.000 something. I mean, you know, but we don't care anymore because it's so small, it doesn't matter. It's like right now, there are dust particles landing on your head. But you know what? As far as the amount of change in your weight, nobody cares. It just doesn't matter. Okay? And if he brushes his hair out as he did, then he's getting dust particles in the air. Okay? Little dead, creepy crawly things. Okay? Most of the dust is little dead, creepy crawly things. Okay? Huh? What? Dust mites. Okay? And other things. But yeah. All right. Now, the beta particle comes out of a a neutron. Comes out of a neutron. Now let's see. This is negatively charged. I'm going to take it out of a neutron, neutrally charged. What do you think we have left over at the end? Something neutrally charged. Take a negative charge out of it. What do you got left? Positive. What has a positive charge and the same mass as a neutron? So we're creating a proton. Every time there's a beta particle emitted, we create a proton. Okay? So the math works out for us. There is really no negative atomic number, but the math works out for us if we assign a -1 atomic mass number to a beta particle. Okay? Does that make sense? Then when we do the math, we put an equation like this, we can get the right thing. Okay? So let's see if I have an example. An example here somewhere. Here we go. Okay, silicon 27. And we're just going to go through beta decay. I could have used carbon 14 because that's really pretty, we have to know about that anyway. -0, -1, beta particle. Okay, so what are we going to have left on the other side? What part are we going to make over here? No? Yeah, what part, if I take a beta particle out, what are we going to have left? So we're going to, what we need is something we add to over here that's going to give us a 14. What do I add to a -1 to get a 14? 15. What element has an atomic number of 15?
Oh, phosphorus.
Thank you. Good job. Good job. Okay. And 27, what do we add 0 to get 27? Trick question. Yes. What do we add 0 to get 27? 27. Okay, so what we have then, if we have beta decay of silicon 27, is phosphorus 27. Got that? Yes? No. Because that's a 0 right there. It doesn't change the mass. What it does is change a neutron into a proton. Neutrons and protons weigh the same, so the mass doesn't change. The mass of that beta particle is so small, when we kick it out, it doesn't really change the mass overall, like I talked about my example of dust particles a while ago. Okay? All right. So silicon 27, beta decay, we get this. Okay? That makes sense? Now, I sort of kind of mentioned carbon 14 a minute ago, and I'm going to come back to that in a minute. First, I want to get to the last particle about, well, actually, a couple particles we know about, but the last nuclear decay particle. This is all about nuclear decay and nuclear radiation. When we spit out these particles, like alpha particles and beta particles, that's called nuclear decay. Okay? When I spit out these alpha particles and beta particles, that's called nuclear decay. Okay, I don't have to write it down for you to write it down, you know. If you don't know what nuclear decay is, you should be writing. Okay? Nuclear decay. Anytime you're getting rid of these particles from the nucleus. And there are other kinds of decay other than these. We're only going to deal with 3 kinds of decay, or 3 kinds of radiation in here. So this is an alpha particle. When I have a lot of alpha particles, I have nuclear radiation. Okay? This is a beta particle. When I have a lot of beta particles, I have beta radiation. Okay? And then when I take an alpha particle out of a substance, that's called nuclear decay. The removal of alpha particles or beta particles or anything else from the nucleus is called nuclear decay. The removal of any of these subatomic particles from the nucleus is called nuclear decay. Okay? It's not that hard, really. Okay? All right, so that's nuclear decay. That's nuclear radiation. Okay? Nuclear radiation is the combination of a bunch of these. Okay? Got it? And the last kind of radiation we're going to talk about is called gamma. Now, we don't call it a gamma particle, although I guess it is kind of a gamma particle. Okay? Gamma radiation is pure electromagnetic radiation. Okay? And nuclear what am I trying to say? Magnetic. What I just said it. No. Electromagnetic radiation. For some reason, I could not say electromagnetic radiation. It just wouldn't come out of my head. Okay? Electromagnetic radiation. There's electromagnetic radiation coming out of the lights in here right now. Okay? It's light. Light is electromagnetic radiation. Okay? Radio waves, electromagnetic radiation. Microwaves, electromagnetic radiation. Radar waves, fill in the blank. X-rays, all that's electromagnetic radiation, just different wavelengths. Very good. Light wavelengths are the kind that we can see anyway. It's all light. The light that we can see is a tiny, tiny, tiny slice out of the whole spectrum of electromagnetic radiation. Okay? Radio waves are on the long end, down below red. Not microwaves. X-rays and gamma rays are above, above the violet end. Okay? Actually violet, indigo, whatever. You know, you've heard Roy G. Biv. Yeah. Okay, the V doesn't exist. Okay, I know that we use that because it sounds better than Roy G. By. I don't know. You know. Yeah. Anyway, it's all right. Because indigo and violet, they kind of look the same anyway. So most guys can't tell the difference. You know, girls know the difference between pink and peach. Guys don't, right? That's probably sexist. I shouldn't say that, but that's true, right? For most high school guys. What? Yeah, guys can't tell the difference between pink and peach.
Yes, you should. They're two different colors.
I agree, they are. I mean, if you tell a guy, oh, I've got a pretty teal dress. What?
Blue.
All right. So I've got a discussion going about something other than chemistry. Anyway.
Darn.
I know. So gamma radiation is all electromagnetic radiation. Electromagnetic radiation. Listen, gamma radiation is the tiniest, smallest wavelengths of electromagnetic radiation. You need to know that. Gamma radiation has the smallest wavelengths of any electromagnetic radiation. You need to know that electromagnetic radiation is light, but the only light we can see is a tiny little slice, way below the wavelength of gamma. Okay, now that's not new stuff. You should have learned that in physical science. Okay, should have learned it in earlier classes anyway, too, as well. All right, so gamma radiation then, electromagnetic radiation, it's light of a really tiny wavelength, really high frequency. Okay, so gamma radiation, we said that alpha particles won't even go through this piece of paper. Gamma radiation will go all the way through you. Okay? It'll go through a thick concrete wall. Well, maybe this thick, really thick concrete walls it won't go through, but this concrete wall outside our room here, yeah, probably most of those would come through there. Okay? You have to have probably like a 3-foot thick solid concrete wall to prevent gamma radiation from penetrating. And the problem is the wall itself is emitting gamma radiation. But anyway, gamma radiation everywhere. All this radiation is everywhere. There's radiation in this room right now. All these radiations are here.
Is there radiation back for you?
Ah, very good question. Here's my point in saying that, okay? Here's my point. That it's not that radiation is bad or good. It's the amount that's a problem. Like anything, okay? Anything can be. Too much water will kill you.
Too much anything will kill you.
Okay?
What?
Too much water will kill you.
Yeah.
You didn't know that? Yeah. You can drink so much water that it flushes out all the ions from your intestinal system and you die. Okay?
Can't openly alone.
A lot of things. You can drown. That's too much water too. Yeah.
How much water is too much?
I have no idea. Ask the trainer next door. Okay? I don't know. All right. The question was, how much water is too much water? I don't know. We have a trainer in the room next door to us over here. Okay, go and ask her. All right. Now, the symbol for gamma. The symbol for gamma is like a script letter L that you spin 180 degrees. Okay? Like a letter L that you, script letter L that you spin 180 degrees. There's gamma. Okay? So if we spin it around 180 degrees, it looks like a script letter L. Okay? All right. Now, if we have gamma radiation, its mass is almost, I mean, you talk about electrons' mass being small. Photons of light do have a mass, but they're so small we don't care about them. And it doesn't change any of the structure of the nucleus, so it's a 0 here too. All right? Huh? Well, I mean, like the dust particles, we don't care. Really? Okay. Now, when uranium goes through alpha decay, it also goes through gamma decay. So if I were writing a complete equation for this, I'd probably write something like this. 238, 92, uranium, alpha decay, and then gamma radiation, and thorium. All right? All right, now those are your forms of nuclear radiation. You need to also know about neutrons, but we know about neutrons, I hope. Their symbol is N. When we write them with a nuclear symbol, the mass of a neutron is, anybody know? What's the mass of a neutron? Same as a proton. What's the mass of a proton? Mass of a proton. 1. 1. Okay? But it doesn't change. I'm sorry, that's the masses down here. Okay? Nope. Protons down. And it's not a proton, so that's a 0. I'm sorry. 1 on top, 0 on the bottom. Okay? All right. Now then, nuclear equations. I've written 3 nuclear equations here. Okay? Everybody got it? I'm going to give you a homework. So you're going to complete these nuclear equations. All right? All right? So you got to know what goes there. Let's see here. What I was going to do, no, I don't want to do that one. Here we go. Nope. I'll find one for, here we go. Good, this is a good one. We just mentioned this one. I'm going to let you finish this part of it here, as well as what goes over here. Okay? All right, that's your homework. Finish those equations. Remember, when you do your homework, as long as you try, okay, you can't just write it down and leave it blank. As long as you actually try, you can fix it later by getting a makeup problem and get all the points back. But if you don't do your homework, you're going to lose 10% a day if you turn it in late. Oh, yeah, I need your interims. Let's stack them right here.